Hello, everybody. Today I'm going to be giving a talk called The Shape of Modified Numerals. And this is work together with Jakub Zimanek at the Institute for Logic, Language and Computation at the University of Amsterdam. So first of all, what the structure of the talk is. So I'm going to just say a little bit about modified numerals in general, then talk about previous literature on the problem, and finally present an RSA model that addresses some of the questions that arose from previous literature. Okay, the phenomenon and the data, first of all. So modified numerals, expressions like less than n and approximately n, where n is a numeral, and intuitively they give information about the size of the intersection between two sets. So for instance, more than 3 cats sleep, more than 3 here is the modified numeral. And then you can imagine that we have the set of cats and the set of sleeping things. And more than 3 cats sleep gives information about the size of the intersection between the set of cats and the set of sleeping things. And namely, it says that there are more than 3 things in that intersection. So in the following, I'm just going to be focusing on more than n type of modified numerals. So this picture is pretty simple, but there are complications. So first of all, the standard Horn account is at odds with modified numerals behavior. So for instance, more than 3 does not implicate not more than 4, even though a collaborative rational speaker could have produced more than 4 if it had been the case. Second, implicatures from more than n depend on the roundness of n. So more than 10, for instance, seems to implicate not more than 20, but it doesn't seem to implicate not more than 13. And prima facie, we can think that it's the reason for this is the difference in roundness between 20 and 13. Third complication is the plausible range of m seems to depend on the magnitude of n. So for instance, more than 10 cats sleep, the real number is probably not 1,010. But if we say more than 25,000 cats sleep, it could be very well 26,000. So a difference of 1,000 is much more likely when the number is 25,000 than when it is 10. Okay, so all of these 3 patterns really are components of a more general problem, which is what is the posterior distribution that we have over the true number after hearing more than n for any given n. Okay, so just to show that this last question is in fact more general than the 3 discussed specific complications, there are various patterns that are all compatible with, there are various posterior distributions that are all compatible with the discussed complication, these 3 points that I made above. So imagine that n is the numeral that you're modifying, and that we have a distribution of, for each n, we have a distribution over the true numeral. One option is that the posterior looks like a normal distribution, well, a discretized version of the normal distribution. So for instance, if you hear more than 11, it could be somewhere about, it could be centered somewhere around 12, but if you hear more than 10, it could be centered maybe somewhere around 15. It could be exponential-like, where we get a decrease, a constant decrease starting with n. And it could be uniform-like, for instance, where you have something that looks like a uniform between n and some higher number, which might depend itself on n. Okay, so in all of these 3 patterns, the 3 complications that I discussed above are in fact satisfied. So more than 11 doesn't need to imply not more than 12, because the shape of the distribution in all of these 3 cases can depend on n. The shape can depend on roundness, and it can depend on the magnitude. So there is the problem of finding the posterior distribution for the numeral is more complex than just answering those three complications that have been posed in previous literature. So there is previous experimental work on finding out what the posterior or given a modified numeral like more than n looks like. So Cummins et al. 2012 is the kind of first big study on this. They have 16 contexts, 2 conditions, range and single number, 1,200 participants, and each context looks something like this. So first they give an information. A newspaper reported the following: numerical expression: people attended the public meeting about the new highway construction project. Question: based on reading this, how many people do you think attended the meeting? And then the range condition asks for a range, and the single condition just asks for a single estimate. There's 2 quantifiers, so more than, less than, 3 levels of roundness, 100, 110, and 93 in decreasing roundness, and 2 predictions. So the rounder the n, the highest the estimate relative to n. And in range condition, typical upper bounds will be the next point on the round scale. Okay, so the results for the single number condition from Cummins et al. 2012, really just focusing on this single number condition here for the 3 cases. And this illustrates it pretty well. So when you hear more than n, and you're asked to produce a single number, you see that the distance from n is greater when you have a very round numeral, so a coarse numeral, than when you have a fine numeral. So you get the effect that was mentioned above. And they also have 2 more experiments, but I'm just gonna ignore them because of time constrictions. So it looks like rounder numbers do indeed lead to higher estimates. Then there's more recent data from Hesse and Benz 2020, who respond directly to Cummins et al. And they tested more numerals, and a different pattern emerged. So tested prior distributions for various contexts. I'm not going to go into detail, but yeah, they just test more numbers, and the effect is not so clear. But there is a clear effect, namely that when you get closer to a round number from below, you have this kind of squeezing of guesses between the n and the round number. So for instance, when you hear 190, more guesses are squeezed between 190 and 200 than you'd expect, given the shape of the other guesses for other numbers. Okay, and they have a series of experiments. They use larger magnitudes as well, in the tens of thousands, and they give an account based on A and S. There are some problems with this, so they don't give a cognitive model of the behavior. They give a partial characterization based on A and S, and the magnitude effects are also explained by the generative model. So A and S doesn't explain why, larger numerals lead to rounder numbers. So for instance, when the true number was greater than 15,000, only 88 out of 1,000 guessed numbers had a roundness of that was smaller than 400, than the roundness of 400. And they do give a proposal for the distribution of production. So they don't have a model of how the participants are actually producing the numbers. So the summary of the situation, there is a question: what is the posterior after hearing more than n? We looked at some pattern that need to be predicted, and presented some experimental evidence from some really good papers that give very rich, interesting data, previous literature. So the proposal here is to use a simple rational speech act model to predict or explain the posterior distribution after hearing more than n. Just very briefly, how do rational speech act models work? Well, there is a rational literal receiver, and they get a signal. They guess among the states compatible given the posterior. Then you have a pragmatic speaker and the pragmatic speaker gets a state and tends to send the signal that is most useful to the literal receiver. So they have in mind the literal receiver and what their posteriors over states will look like, and they pick a signal that's useful for each state. And then you have a pragmatic receiver that gets a signal and then does Bayesian updating based on the probabilities of production of the pragmatic speaker. So they simulate the pragmatic speaker, the pragmatic sender, and think what is most likely doing Bayesian update. Okay, then you can represent this in terms of arrays. And the crucial thing here is that if utterance 1 is compatible with state 1 and state 2, and utterance 2 is only compatible with state 1, then as you calculate, as you go through the layers of recursive mind reading, when you get to the pragmatic receiver, you have something that looks like a scalar implicature. So state 1 is not likely given utterance 1 because utterance 2 would be more useful than utterance 1 given state 1. So it is used by the pragmatic speaker more often. Okay, so instead of 3 states and 3 signals, we have 10,000 states and 10,000 signals. So we simulate the full scale of numerals. We let the production prior depend on roundness, so that more round numbers have a higher probability of being produced by the speaker. The speaker just prefers to produce round numbers in a way that I'm not going to discuss in detail here. And we just take the roundness levels as calculated in Hesse and Benz 2020. We specify a geometric prior over states for L0 and L1, so they have an prior expectation over states, and we use different priors for small and large modified numerals that look like this. But this is not super important. So the prediction for a pragmatic listener is that, so here in each row you have a signal, so more than 30, more than 35 here, more than 40, and so on. And this is another way of visualizing it. So this is more than 100, then more than 110. And what you see is that as you approach round numbers, so in this case 150, you get this squeezing effect where numbers between n and the modified and the immediately successive round number are more likely than anything higher than the round number compared to other to the shape of the distribution for other numbers. Okay, and the effect is stronger when you have a more round number. So in this case, 200 rather than 150 here. So the two crucial predictions that are explained by the model and corresponds to what we see in the experimental data. The posterior is exponential-like, and the squeezing effect, you get the squeezing effect as a function of roundness. Okay, so the 3 patterns from earlier, more than 3 does not implicate not more than 4. The implicature is weaker for low roundness numerals, so that's what we see from the model. More than 10 implicates not more than 20, although not more than 13. So again, the squeezing effect. And plausible range of M depends on the magnitude of N. So in the model, this depends on the shape of the prior. And can be justified either by ANS or by some implied generative model, for instance, Poisson distribution for the examples that were given in the experiment. But we are working on a more principled approach to this problem. So stay tuned for further work on this. And then here there's some stuff that I'm going to jump for because there is no time. But the conclusions are modified numerals seem easy, but there are some complications. Previous data has shown interesting pattern in their behavior, and a simple RSA model can model various aspects of the data. Thank you.